So the rate of change in linear and quadratic functions is what we're going to focus on in topic 1.3. Linear functions, it's really pretty straightforward because linear functions are the ones where you found a slope previous to this class. So for any linear function, the average rate of change over any length input value interval is constant. It has the same slope or the same rate of change like literally the whole time from negative infinity to infinity because it's one line going the same direction the whole time. Meaning the average rate of change changes at a rate of 0. It's not changing. It is constant. For a quadratic function, on the other hand, the average rate of change over consecutive equal length input value intervals, not any length, but consecutive equal length input value intervals, meaning counts by ones, counts by twos, counts by threes, we're staying the same the whole time. It can be given by a linear function itself, which means that the average rate of change changes at a constant rate. So let's get that vocabulary right, because this is very confusing. It feels like we're using the same words over and over again. We are, and they mean different things. A linear function has a constant rate of change, meaning the change in the rate of change is 0. A quadratic function has a rate of change that changes at a constant rate, meaning it's a linear function, not 0. Okay? Let me say it again. I get it. It's weird. It's weird. So linear functions, they change at a constant rate. Same slope the whole time. Yeah? That makes sense. Slope is the same. That's a property of linear functions. Meaning the change in the rate of change is nothing. We're never changing the rate of change for a linear function. A quadratic function, though, doesn't have the same rate of change the whole time because it goes down and then goes up. So you'd have like negative slopes and then positive slopes. But the change in the rate of change is constant the whole time. The change in the rate of change is constant. Yeah, I'm saying the word change a lot on purpose. The change in the rate of change is constant versus the rate of change being constant. Completely different things. Let's see a couple examples before we maybe ask some questions that might be helpful. Example 1 says the table on below, LOL, that's embarrassing. The table below gives selected values of the function f of x. Explain why f of x is not a linear function. Okay, let's check out the average rates of changes over these intervals. This is any interval because a linear function should be constant over any interval. If I'm finding the average rate of change between 1 and 2, meaning I'm finding the average rate of change here, using the average rate of change formula, I would do f of 2 minus f of 4 all over 2, sorry, not f of 4, f of 1 over 2 minus 1, okay? Outputs on top, inputs on bottom, we subtract them, yeah? 7 minus 4 is 3. 2 minus 1 is 1, so that number is 3. The rate of change between 1 and 2 for this function is 3. Rise 3, run 1, right? Slope, rate of change. If we find the average rate of change between the next two parts of this interval, we'd be doing 10 minus 7 over 4 minus 2. 3 on top, but what's on bottom? 2, uh-oh. Let's check the last one. This is 13 minus 10 over 8 minus 4. This is the average rate of change formula, outputs over inputs, which means I have 3 on top and 4 on bottom. So are the average rates of changes the same? No, that means this is not a linear function. The sentence we would want to write to explain this, to provide an example or an explanation of why, is we'd say, f of x is not a linear function because over any interval, the average rate of change is not constant. And the average rate of change must be constant over any interval. Doesn't matter what sort of inputs we have. Over any interval, the average rate of change should be constant. Is that a little bit clearer what I mean by that? Yeah, if the average rate of change is not the same every time, it's definitely not linear. If we look at a quadratic example here, okay, consider the quadratic function g of x equal to x squared. This is our parent function, right? Complete the table of values for g of x over consecutive equal length input value intervals below. Then complete the table for the average rates of change of g of x for each consecutive interval. What do you notice about the average rates of changes over these consecutive equal length input value intervals? You're going to hear me say that a lot, so let me explain what that means. When I'm talking about consecutive equal length input value intervals, it says it 3 times in this question. What I mean is the input values here must change by the same number for us to be able to compare for quadratics. It didn't matter for linear functions. If you notice, we didn't change by the same numbers in our table here. It shouldn't matter for linear functions because it's over any interval, but we do need to make sure we're counting by the same number in our tables when we deal with other functions. So do you see how here it's all plus 2's all the way down? Great, moving on. Let's make our table of values. So if I were to plug -3 into the g function, that means I'm doing -3 squared. What's -3 squared? It's positive 9 though, because negative times negative is positive. I heard some people say that and I heard the negatives. Okay, what about -1 squared? How about 1 squared? How about 3 squared? How about 5 squared? Okay, great. So now we're going to show our work a little bit more like robustly here. Over the interval from -3 to -1, which is between these 2 points, yeah? Let's calculate the average rate of change in this table. So following the formulas for the interval from -3 to -1, I would use the output at -1, which is 1, and subtract the output at -3, which is 9, all over -1 minus -3. If you can already change minus and minus to plus, that's fine. I'm writing it on purpose like this so nobody's confused. There are minuses in this formula. 1 minus 9 is -8. -1 minus -3, which is -1 plus 3, is 2, which means the average rate of change in this interval is -4. Do we see what I did here? Okay, the only thing that's different from what we did last time to this time is that I'm not putting the g of -1 minus the g of -3 in the formula just because there's not enough room. I do want that most of the time. Can you fill out the rest of this table for me and find all of the average rates of changes on those particular intervals? That second interval from -1 to 1, what is the average rate of change?
0.
And then the next one, and then the next one. Okay, so what are some things that we are realizing, noticing these average rates of change on this interval? Is it linear? Why not? The average rate of change is not constant. They need to be the same number every single time when you find the average rates of change for it to be linear. But here's what I want you to look at. Let's look at these average rates of changes. If I was going between -4 and 0, how do I change from -4 to 0? How about from 0 to 4? How about from 4 to 8? Oh my gosh, so that means we are changing at a constant rate. It's constantly going up by 4. So our average rate of change is changing at a constant rate. Not the function changing at a constant rate, but our average rates of changes are changing at a constant rate. In Algebra 2, you would have called this the second differences. That's still what we're finding. You just called them second differences before. We're calling it the change in the average rate of change. Same vibe. So let's write a conclusion sentence here. It says the average rates of change of g of x over consecutive, so in order, equal length, meaning they go up by 2 every time or whatever they go up by, over consecutive equal length input value intervals, the average rate of change are not constant. You guys told me that, so we know it's not linear. Instead, they being the average rates of changes, are changing at a constant rate of 4. No. It's fine. We'll be okay. You will have to provide me examples and reasoning throughout this class, but this is a whole paragraph, okay? I got you. Therefore, the rates of change of the quadratic function of g of x are given by a linear function. So we could graph the rates of changes, and the rates of changes would create a smooth, straight line. So let's read the whole sentence one more again now that we've got it all filled in to make sure we understand what we just wrote down. The average rates of change of g of x, these numbers, over consecutive equal length input value intervals, these guys. These are not constant. Instead, they are changing at a constant rate of 4. Therefore, these average rates of changes are given by a linear function. Linear functions have constant rates of changes. Okay? It's confusing a little bit until you handle whether we're talking about the function or the average rate of change of the function. I totally get it. Any major questions before we go to the back of this? Okay, here's the sentences I do want you to be able to write today. We're going to have 3 examples here, and it says we have these tables for selected various functions. For each table, we're going to determine if the function could be linear, quadratic, or neither, and give a reason for our answer. So I'm going to do the first one, and you guys will have the next 2. If we're finding the average rates of change between each of these intervals, we can kind of use a little shortcut like I did on that very first problem and write down the average rate of change just to the side of the table. The average rate of change over these intervals would be 1 minus 0 over 2 minus 1, which would be 1 over 1. That's 1. Do I follow? Okay. The next interval would be 4 minus 1 over 3 minus 2, which is 3 over 1. That means that this is 3. The average rate of change between 3 and 4, we would calculate by doing 9 minus 4 over 4 minus 3. That would be 5 over 1, or 5. We have calculated the average rates of changes over these intervals. My question for you is, are those numbers the same?
No.
So can it be linear?
No.
Are those numbers changing at a constant rate?
No.
Ooh, I heard both. How do you go from 1 to 3? How do you go from 3 to 5? That's the same number, yeah? They are changing at a constant rate. So how we answer this question for me today is that this function could be quadratic because the average rate of change changes at a constant rate. It is quadratic because the average rate of change, the numbers we calculated, are changing at a constant rate. In fact, they're changing at a rate of +2. A little bonus information. If this was linear, what sort of explanation would you use to tell me that it's linear?
Changes at a constant rate of nothing, 0.
I accept. I would prefer you to just say it is constant. The average rate of change is constant. But also that would totally work. Okay, you're going to have the next 2 tables to practice and try. If you were hanging on by dear life for the average rate of change, check with people next to you to make sure you understand where I'm getting these numbers from. But go ahead and try the next 2 tables. You got this. All right, check your average rates of changes here. I've got them all written down. Is this what we calculated for all those individual average rates of changes? Yay, let's draw some conclusions. For that center table, the function could be what? Linear. Why? The average rate of change is constant. It's the same number the whole time. Okay? We're going to try to avoid using the word it in this class. It's ambiguous. I need to know what we're talking about. Because when you say it is constant, I could be like, is the function constant? You're talking about the average rate of change.
Should we have also put that the average rate of change is 0? Like it's not changing.
You would have to say the change in the average rate of change is 0. Yeah, I know, that's different. Because the average rate of change being 0 means it's a flat line.
Yeah.
That's not necessarily what's happening right here. Good question, though. Good question. How about for the last one? We have these average rates of changes from 1, there's 1, and then 1/2, and then 0. So this function could be what? It is actually quadratic. Whoa, let's talk about the changes in the average rates of changes. And I know fractions freak everybody out. How do I go from 1 to 1/2? Minus 1/2. How do I go from 1/2 to 0? Oh my gosh, these are actually changing at a constant rate. So it is quadratic because the average rate of change changes at a constant rate. That rate just happens to be -1/2. Yeah, so you got to make sure you're looking at those patterns in the, in the average rates of changes. What's cool about the average rate of change, though, is it actually gives us a lot of information about the concavity of a graph. That way if we don't happen to have a picture of the graph, and we're on the non-calculator portion of our test where we can't create a graph for our function, we can still tell the concavity of the graph. So let's review a little bit about concavity. If a graph is concave up, that means that the average rate of change over equal length input value intervals, that means that it's increasing. Oops. Can I get a pen, please? Okay, so this is our increasing average rate of change because it's concave up. Now again, this is confusing to understand because when we're looking at a concave up graph, there's two sides of it, right? We've discussed this before. I'm going to zoom in a little bit so I can color more accurately. On this side of this parabola, would you say that the function is increasing or decreasing? Decreasing. So I'm going to add the color for decreasing. So for me, that's always been red. Wow, this is the worst drawing I've ever done. And on the other side, how would you describe that function? Increasing. So we're going to add some words to be able to describe the average rate of change due to concavity. What we're going to change here, or not change, but add in our vocabulary, is that the left side of this graph that is both decreasing and concave up, that means that the average rate of change is decreasing at an increasing rate. Because it is going down, but it is increasing, so the average rate of change has an increasing rate. I think I said this wrong, and I'm so sorry. I just messed everybody up. The function, not the average rate of change. I can't fit the word function here. The function, I know, here I am also messing you up. The function is decreasing at an increasing rate. I knew that felt weird when I said it out loud. But when you turn that corner after that minimum value, the function is now increasing, but it is increasing at an increasing rate because it's still concave up.
It's increasingly.
Correct. Now let me explain this a little bit. So I'm gonna hold my hands up here because this doesn't really make sense when you first see it. You're like, how can it be decreasing at an increasing rate? So if I were making tangent lines, I'm gonna use my hand to be the tangent line. What kind of slope would be the tangent line right here? Negative, and it's super negative. It's pretty steep, right? What about down here? Is it still negative?
Yeah.
Is it as steep? No, so that's a bigger number. It's increasing. What about here? Still negative, but is it super steep? No, it's an increasing number. When I get here, now I'm increasing, and I'm slowly getting steeper, meaning I'm increasing the average rate of change. So even though we're decreasing, going down, it's at an increasing rate. Let's try this again for concave down. Let's see if I can get it right the first time. For a concave down graph, that means that the average rate of change, I forgot the word rate there. That is so embarrassing. Y'all didn't even let me, yikes. Okay, put the word rate here. The average rate of change, over equal length input value intervals. For this side, it is decreasing. The average rate of change is decreasing. Yeah, so we're going to add those words in just like we did on the side. Here's all of our concave down graph. Do a little bit better on my highlighting this time. And I think it's pretty clear that we know this left side is increasing and the right side is decreasing. So let's talk about this function in a different way. On the left side, the function, let's see if I can write it better this time. The function is increasing, because it's going up, at a decreasing rate. If this was measuring speed, it's slowing down. Then we go to the other side, and this time the function is decreasing at a decreasing rate. because it's concave down, so the average rate of change is getting smaller. We're getting steeper negative. So it's a decreasing rate. Let me go again with my hands with these tangent lines because it might be a little bit helpful. If we start here, I have positive slopes, yeah? Okay, positive slope, but it's getting less positive, it's getting flatter. Then we get here and we start going down. It's pretty flat at first, and as we go down, it gets steeper and steeper and steeper, which means those numbers are smaller. So it's a decreasing rate. But since we know this occurs on the graph, we can use the rates of changes in tables to determine if a graph would be concave up or concave down. So follow along with me. We'll ask questions after the first one. We're going to have selected values for these three functions in the table. For each function, determine if the function could be concave up, concave down, or neither over its domain, and give a reason for your answer. So we're going to calculate the average rates of change for each of these intervals. We've done this already today. We feel like we can do it. Here we go. This would be 1 minus 4 over 1.1 minus 1, which is negative 3 over 0.1. Does anyone remember, without a calculator, what negative 3 over 0.1 would be? In my brain, here's how my brain does this. I don't remember the ways you've been taught decimals. If I want to move this over once, that means I have to move this over once. This is negative 30 over 1, which is negative 30. If I do this again, okay, I go here, I have negative 1 minus 1 over 1.2 minus 1.1, which ends up being negative 2 over 0.1. Using that same idea, move the bottom decimal once, move the top decimal once. What does that become? Negative 20 over 1, which is negative 20. Same vibe, negative 2 minus negative 1 over 1.3 minus 1.2, which is negative 1 over 0.1. Draw a conclusion there. What is negative 1 over 0.1? Negative 10. Okay. Review question from the top. Could this be linear? Why not? The rate of change is not constant. Yes, okay. But now the question is, could this graph be concave up or concave down? Are those numbers, the rates of change numbers, are they getting bigger or getting smaller? They're getting bigger, which means the graph is going to be concave up, again, because the average rate of change is increasing. If the average rate of change is increasing, that means we're concave up. Those numbers are getting bigger. So our function at this point is concave up. The average rate of change is increasing. Can I let you try the other two? I'm going to not give you any explanation on how to explain the rest of them. I want to see what conclusions we draw here. But go ahead and try the second and third tables. Got the average rates of changes on the board. Let's draw some conclusions. What's happening in the M of X table, the middle table? What's constant? The average rate of change is constant. So what does that mean for concavity? It's a linear function, which means there is no concavity. So it is neither concave up or concave down. Because, like you guys just said, because the average rate of change is constant, that does mean that this is a linear function. Very good. We drew the right conclusions. Linear functions do not have concavity. They have a constant rate of change. And it's neither increasing nor decreasing. Now what about the P of X table, the last one? Concave down, why? Because what's decreasing? The average rate of change. Yeah, we got to get used to saying exactly what we're talking about, especially in questions dealing with functions and concavity. Because the average rate of change is decreasing. Very good. Any major lingering questions we want to ask before we get into independent practice time? No. Okay, fabulous.